So what we have learned so far, we start talking about different applications of ODEs. The very first model that we talked about was the population growth or decay. In general, we talked about the exponential growth and decay. So remember that in this case, we said that the rate of change of the population with respect to time is proportional to the population itself. So the rate of change of the population or the amount that you're dealing with is proportional to the population itself. So when we have a question like this, when we are dealing with exponential growth and decay, as you saw, it's a separable differential equation. Separable. So dp over p is equal to k dt. If we can take the integral of both sides, we get ln of absolute value of p equals to kt plus constant of integration. Well, in this case, we say that p is equal to plus minus e2, for example, let's call it c sub 1, e2 kt. Now, this guy, p, becomes c e2 kt. And remember that p as a population is a function dependent on free variable t. So we found a model for exponential growth and decay that gives us the general solution. C was called the initial value, and K is the constant of proportionality. In different cases, in different examples, we're interested in finding C and also K, so we can actually build this mathematical model. Other than the exponential growth and decay, we talked about the, for example that was about radioactive decay. And then we introduced the Newton's law of cooling, also slash warming. Newton's law of cooling. We can just generalize the idea to warming as well. So in this case, we remember that we had the following case. If we have the temperature, the rate of change of the temperature with respect to time is proportional to, well, here you have the temperature minus the temperature of the environment. For example, you can denote it by T sub M. So this guy is the temperature of the room or the environment that you have. Again, here you have a separable differential equation. We can divide both sides by T minus Tm, and on the right-hand side, you have K dt. By taking the integral of both sides, we get ln of absolute value of T minus T sub m, which is equal to Kt plus C sub 1. The same process. Using the definition of ln, T minus Tm becomes plus minus e to C sub 1, e to Kt, or T is equal to Tm plus C e to power Kt. Like the example of the time of death that you actually modeled using the Newton's law of cooling. Today, we're going to continue the process talking about the applications of ODE. In this case, we're going to talk about mixing problem. Now, let us take a look at the following example. We have a mixing problem that can be modeled using differential equations. In this example, we have the following case. The mixing of two salt solutions is our case here. So mixing problem. Suppose a large mixing tank initially holds 300 gallons of brine, which is a combination of salt, another brine, is pumped into tank at a rate of 3 gallons per minute. The concentration of salt in this inflow is 2 pounds per gallon. When the solution in tank is very strict, it is pumped out of the tank at the same rate. At the same rate as it was entering. Suppose A of T denotes the amount of salt in the tank at time T. So how do we model A of T? That's the question that we want to answer. What is the mathematical model for A of T? Very well. So what we can do here, we can use the differential equation to set this up. But how? The rate of change of the amount of salt in the tank with respect to time can be formulated as the input rate of salt minus the output rate of salt. So input rate of salt minus the output rate of salt is the rate of change of the salt in the tank with respect to time. But how do we formulate the input rate of salt? Let us call input rate of salt R sub IN and the output rate of salt R sub out. To define the input rate of salt and the output rate of salt, we have the concentration of salt. Take a look at this. R sub in, input rate of salt, is equal to the concentration of salt in inflow times the input rate of brine. Because your brine includes salt. And also the output rate of salt, or sub out, is, well, the same logic, the concentration of salt in outflow, whatever is getting out of the tank, times its rate, output rate of brine. So what information do we have here? Let us read the question. The question says, our tank initially holds 300 gallons of brine. Okay, another brine is pumped into the tank at the rate of 3 gallons per minute. 3 gallons per minute. So what is this? It is the input rate of brine, 3 gallons per minute. Also, question says, hey, it's going to be the same rate for output rate of brine. So we're going to copy down 3 gallons per minute for the output rate of brine as well. What else do we have? The concentration of salt in this inflow is 2 pounds per gallon. Okay. The concentration of salt in the inflow, 2 pounds per gallon. Very well. So R sub I, or the input rate of salt, is 2 times 3, which is just 6. 6 pounds per minute. So 6 pounds per minute. What about the output rate of salt? The concentration of salt in the outflow. Well, what information do we have? We know that initially the tank holds 300 gallons of brine. So the concentration of salt in the outflow is 80 divided by 300 pounds per gallon. If you multiply these two, you get 80 divided by 100. So we found all the information that we need. The input rate of salt and the output rate of salt. Let's just substitute them here. We have the rate of change of the amount of salt in the tank equals to 6 minus 80 divided by 100. So we have a differential equation. How do we solve this differential equation? So first of all, here, if you take the common denominator between these two, you get dA dt equals to 600 minus 80 divided by 100, which is obviously a separable differential equation. Well, you can write this in linear form, and of course, you can solve it using linear method as well. So this guy becomes dA divided by 600 minus A equals to dt divided by 100. Now, since it's separable, take the integral of both sides. So here we get a negative ln of absolute value of 600 minus A equals to t divided by 100 plus a constant of integration. Very well, we can continue this process. Here you can take the common denominator between these two. You can flip this, or you can just write down ln of absolute value of 600 minus A equals to negative t over 100 minus c sub 1 or c sub 2 So here you have 600 minus a equals to e to power negative t over 100 and plus minus e to power c sub 2 or just c. So a is equal to 600 minus c e to negative t divided by 100. This is the mathematical model that we have for this mixing problem.